Okay, so let's continue. So what we want to do now is to study the case where we have frame errors. And for simplicity, we will assume that acknowledgements are transmitted error-free. And in most cases, we can justify this by the following: is to say that the frame is typically much larger than the acknowledgement, and if there are independent bit errors on the channel, then the probability for an information frame to be in error is much higher than the probability that an acknowledgement is in error. Right? So let's just do that for simplicity of deriving these results. And again, we're not interested here in making a completely general and analysis, but rather to capture the broad qualities of these ARQ protocols. So let's start with the simplest one and stop and wait and try to figure out how long time does it take to deliver a frame when we have frame errors. And to do that, we introduce this variable nt, which is the number of transmission it takes to complete a transmission, and that's a random variable. And if we think that frame errors are independent of each other, the expected value of that random variable is 1 over pf, 1 over 1 minus pf, and we will use that later on. Okay, now, so let's draw a timing diagram and see what's going on here for stop and wait. Okay. So at some point in time, and let's put it at 0, we start to transmit the frame. So we basically are here in the diagram, and then we transmit the frame. We start transmitting frame here. Okay, so the first transmission of frame number 1 starts here. And then after some time, it arrives at the receiver. Okay. When we transmit the frame, we also start a timeout counter that expires at this point. So this point in time, when the frame arrives, that's here in the diagram. So we see that that happens after 1 propagation time. It's not exactly important for the analysis that it happens exactly here, but it happens after some time. And then after some time, the receiver would get the acknowledgement that everything has worked out well. So maybe we have the turnaround time to be somewhere here. Okay, so this is the turnaround time, and this is the timeout. Okay. Now, suppose that this packet is actually not received, so it's in error here. Then nothing will happen until the timer expires, so after this timeout. And then a new transmission will take place, and we will start a new timeout counter, and the packet will arrive somewhere here in the middle after some time. And for illustration, we'll just put in the reaction time and the turnaround time here again. Okay, and now suppose that this one was also not received. Then a new packet will be transmitted and so forth. So this will continue for a time until the last one, which is successful. That frame will actually be delivered here. Okay. So the total time it takes to deliver this frame is from when the first attempt is initiated until it's acknowledged at the receiver. So at this point in time, is when transmission of the next frame is possible. Okay. So between the time 0 and this time, the transmitter is busy delivering frame number 1, and it cannot start to transmit frame number 2. Okay. So the total time it takes from start to end here consists of a number of failed attempts. Remember that NT is the total number of times we transmit the frame. So it's NT minus 1 failed attempts, and all of these will take this amount of time. And it's NT minus 1 times the timeout duration. These are for all the failed attempts. And then there is one time T0 for the final and successful attempt. So the total time it takes to transmit this, TSW, is NT minus 1 times T out plus T0. Okay, so let's go through the timing diagram once more because it's important to understand its details here. So the idea here is that we transmit a number of frames, the same frame, frame number 1, and we transmit this NT times, where NT is a random variable. Okay? That means that we transmit NT minus 1 failed attempts before we transmit the final successful attempt. For each failed attempt, it will take time T out before we can initiate the new transmission. So there will be NT minus 1 T out. That's the time it takes for all the failed attempts. And then it will be 1 T0 at the end for the successful attempt. And the successful attempt, if this is the successful attempt, then it starts here, the frame is arriving, and the ACK is arriving, and at this point in time, the transmitter can start to send the next frame. Okay. Any questions? Okay. To avoid unnecessary retransmissions, we put the timeout always greater or equal to T0, right? Because there is no meaning in transmitting a new frame, or rather it's unnecessary to transmit a new frame until we have waited at least T0 seconds, because to give the ACK a chance to arrive. Okay. So the timeout is greater than T0. Then the expected value of the time it takes to deliver a frame, which is this TSW. It's a random variable. It's random because NT is random. Okay. The expected value of that is simply the expected value of NT minus 1 times T out plus T0. Just take the expected value of this and then take out T out, which is deterministic, and T0 is also deterministic, so it's not affected by the expectation. And this we can write, this we, actually it's wrong here. Or rather it's not wrong, but this is what we want, okay? The expected value of nt minus 1 is pf divided by 1 minus pf. So here we get this pf 1 minus pf times t out plus t0. Okay. And for highest efficiency, we want to make this number as small as possible, right? We want this time it takes to deliver a frame to be as small as possible. So what can we do? Well, our only design parameters is basically t out here. Okay, so the time, the expiration of the timeout. T0 is given by, you know, all these physical properties that we have here. So it's not under our control. But we can make this small. So we choose this to be equal to T0 for maximum efficiency. Right? And then this is simply T0 1 minus PF, if I got that right. Let's see. T0, yeah. So if we put this equal to T0, put that on the same ratio, then we get T0 1 minus PF here. Okay, and then the effective rate for stop and wait is then NF minus NO. These are the number of information bits in the frame, okay, useful bits in the frame. And then we divide through by the expected value of the time it takes to transmit this, which we have calculated to be T0 1 minus PF. So here we get 1 minus PF NF minus NO divided by T0, like this. And this final part here, NF minus NO divided by T0, is the effective rate we get when we have no errors. So this is the effective rate for stop and wait with 0 errors. So this is the best we can hope for. So we see that the effective rate when we have errors is the effective rate when we have no errors multiplied with 1 minus PF. Okay, so let's make a sanity check here. If we have no errors, then PF is equal to 0, and we recover, then the effective rate is equal to the effective rate when we have 0 errors, which is true. If every frame that we transmit is in error, then PF is equal to 1, and then the effective rate is 0, which is also makes sense. You know, we transmit, but it never goes through. Okay, so the sanity check here is okay. And then if we want to compute the effective the efficiency of stop and wait when we have errors, since we have this factor in front of the effective rate, that factor will be also in front of the efficiency. So 1 minus PF of the efficiency of stop and wait when we have 0 errors. So any questions on this derivation? So the key thing here is to draw up this timing diagram and figure out what's going on. Okay. And the idea is what we're looking for is a variable that tells us how much time does it take to deliver a frame. And then in stop and wait, we deliver frame by frame. So we can basically take TSW as the time between when we start the transmission of a frame until the time instance when we can start to transmit the next frame. Right? Because at this point in time, the whole thing repeats itself, now with a new frame. Okay. Now, this time it takes to deliver a frame depends on this random variable nt. which depends on, how many errors we have in a row, so forth. Right? So the time it takes to deliver a particular frame will be random. But on the average, the time it takes to deliver a frame is the expected value of TSW, which we then can calculate to be this. And then it's just algebra to put everything together at the end. Okay? All right. So let's do this now for go back n and selective repeat also. And the idea is similar as before. We draw up a timing diagram and figure out what time it takes to deliver a frame in go back n, and then see that this is random, take the expected value of that, and use that to calculate the effective rate and efficiency. So let's do this for now go back n. So at some point in time, we are transmitting frame number 1, and it arrives maybe at this point in time. Okay, so here we have frame number 1. Now, for the analysis here, we need to say that all previous frames have been received correctly, or we can think of this as being the first frame that we ever transmit. Okay? And that is because errors that have happened in the past will actually affect whether this will be delivered or not. But let's assume that all the packets previously have been delivered correctly. Okay? And we're just interested in following frame number 1 through the chain here. Okay, so frame number 1, suppose that is then received in error. Okay. So what's going to happen then is that we have a timeout. That will cause this frame to be retransmitted at some later time, and then it will be arriving at the receiver here. Okay. Now, suppose that this one is also broken, then it will continue with these timeouts until the frame is actually delivered. Okay. So the time from when it arrived for the first time at the receiver to the time when it first arrives error-free at the receiver, this will depend on how many consecutive errors we have. Right? And the number of consecutive errors we have is nt minus 1. Okay. These are the number of errors that we make in consecutively, and therefore the time from this point in the diagram to this point in the diagram is nt minus 1 times timeout. Okay. And then we have to wait until the full frame has been received until we can say that we're done with frame number 1. Okay. So the total time we spend on frame number 1, TGBN, go back n, is nt minus 1 times t out plus tf. Okay. Now, frame number 2 will follow here, right? Because in go back n, we transmit frames consecutively after each other. So frame number 2 will arrive here if we continuously transmit frames. And here is the first time that frame number 2 is possible to receive, right? Because even if frame 2 previously have been decoded correctly has been thrown away because the receiver can only store one packet and the receiver is busy getting frame number 1. Okay. So this is the first time that frame number 2 can be picked up by the receiver, which is exactly the same situation we were here. This is the first time frame number 1 can be picked up by the receiver. So this is actually the cycle for one frame. Okay? And if we want to be complete here, we can say that here is when frame 0 was delivered correctly and accepted by the receiver. Okay, and then if we look at this, the time for go back n, we see that it's nt minus 1 times t out. This is a random variable, and then it's plus tf. Very similar to what we had in stop and wait, where we have nt minus 1 times t out plus t0. So the only difference here is t0 and tf. But it makes a huge difference when t0 is much larger than tf. Okay, which is exactly the case when we want to use go back n. Okay. So for go back n, tf is typically much larger than t0. And this gives the performance gain in go back n. Okay. So let's quantify that in numbers also. First of all, timeout for go back n, it has to do with how many packets we can transmit on the channel before we can get an acknowledgement. So we do that, we take t0 and we do divide by tf and we round that up, and that is what we call and multiply with tf. This is the timeout. And this number here, t0 divided by tf and rounded up, is what we call n. So n is the number of frames that we can transmit in succession before we get an acknowledgement. Okay. So to avoid idle transmitter, we set the send size window equal to n. Okay. So this is what we started the lecture today by stating these rules. So if you forgot about that, you can look it up later. But anyways, we then choose the timeout according to this. So now the expected value of the time it takes for go back n to complete the delivery of one packet is the expected value of this tGBN, which is then just the expected value of nt minus 1 times t out. Expected value of nt minus 1 times t out, and we replace t out with n times tf. And then we should add on the last tf here, this one. The expected value of nt minus 1 is pf divided by 1 minus pf. So here we have pf 1 minus pf nt n times tf plus tf, which we can simplify to be tf times pf n minus 1 plus 1 divided by 1 minus pf. That's just algebra there. Okay, and the effective rate for go back n is then the number of bits we have in a frame, nf minus no divided by the time it takes to complete this, which is the expected value of t gbn, which we can write now as we break out nf in the numerator here, and 1 minus no divided by nf. And then we divide through by this result, where we get tf times pf n minus 1 plus 1. And then we should divide by 1 minus pf. So we put this in the numerator here. As this. Okay, so it's just algebra here. And what we recognize here, what is this? nf divided by tf. Let's go back here. Tf is nf divided by r, or r is nf divided by tf. Okay, so this is just the data rate of the layer below us, which means that the effective rate is the data rate of the layer below us multiplied with some factor, and that factor is simply the efficiency of stop and wait here. Okay. So is this good efficiency or not? Well, it depends, right? Let's look at it. This factor, 1 minus no divided by nf, okay, this has to do with the number of overhead bits in our frame, and this is the size of the frame. So this is not so much we can do about. This will be the same regardless of which protocol we use. As a matter of fact, this is the best efficiency we can ever hope for with a perfect protocol, where there are no errors and so forth. 1 minus pf has to do with the channel. Okay, so we have this penalty that we had before also. Remember that we had this penalty 1 minus pf also in stop and wait. Okay. So this is to be expected also. But the killer for this protocol is the denominator here. It's pf times n minus 1 plus 1. And n here is the ratio between T0 and Tf. And n should be large if we want to use go back n. Because if this is a small number, then stop and wait is a good protocol. So the whole rationale to go back n is when T0 is large compared to Tf. Okay? When T0 is large compared to Tf, that is when n is large. Okay, so n here is a relatively large number. And then we see that as pf increases, the denominator becomes large and the efficiency goes to 0 quite quickly. However, when we have a good channel, when pf is small, let's say pf equal to 0, then the denominator is 1, right? The first term here is 0 plus 1, so it's 1. And this factor here is also 1. And then the efficiency is 1 minus no over nf, which is the best we can hope for. So go back n is excellent when we have low probability of error. It's very bad when we have a high probability of error. You see this? Okay. So what to do when n is large and we have a high probability of error? What should we do then? Yes, very good. We changed strategy. So luckily we have one more protocol, right? Selective repeat. Let's see how that works. So we start with the same idea. We draw here a timing diagram of what's going on. So at some point in time, frame number 1 will arrive, right? So this is frame number 1. And we can now look at frame number 1 independent of the others, because now the receiver will store out of order received packets. So if frame number 1 arrives error-free, it will be stored and eventually delivered. Okay. Now, suppose it's not received, that is some error, then at some point later, we will transmit packet number 1 again. Okay. And suppose that this is not correct either, then at some point later, we will transmit it again, and then it will be received. Okay. So a packet will occupy the channel for nt times tf seconds before it's delivered. Okay. We had nt minus 1 errors and 1 correct reception, like this. Okay. And this is true for any number, any sequence number. So if it's true for 1, it's true for 2. It will have different nt because nt is a random variable. It differs from packet with, from sequence number to sequence number, right? But a packet will occupy the channel for this time, and let's call this TSR. It's nt times tf. And therefore, expected value of TSR is the expected value of nt times tf, which is 1 over 1 minus pf times tf. And the effective rate for selective repeat is then nf minus no divided by tf, and everything multiplied with 1 minus pf, like this. And we can write this as nf divided by tf, 1 minus no divided by nf, times 1 minus pf, like this. And again, nf divided by tf is equal to r, which means that the factor that follows it is the efficiency of selective repeat. Okay. So let's now compare this with the result for go back n. And we see that the efficiency for selective repeat is similar to the select efficiency for stop and wait, except that we don't have the denominator left. We only have the numerator, right? 1 minus NO divided by NF. This is something which is the same for all protocols. And then we have this 1 minus PF, which is the factor that it seems to be unavoidable when we have errors. But at least we don't have the penalty of the denominator here. So this is a good strategy when we have errors. Okay, and N is large. Okay, any questions on this final derivation? Okay. So what we have done now is we have calculated the efficiency for our basic 3 protocols, stop and wait, go back N, and then select the repeat. But so let's do some engineering around this. When should we select the different protocols? Well, it has to do with, let me see, let me get some space for this. So the things we have which are concerns is the delay bandwidth product. Okay, and what was that again? Well, it has to do with the ratio between T0 and TF. Okay, T0 is the time it takes to transmit one frame until we can receive its acknowledgement, okay, with some processing delays and so forth. So this is one concern. The other concern we have is frame errors. Okay. So now suppose the delay bandwidth product is low and the probability of error is low. Which protocol would you use? There are 3 choices: stop and wait, go back and select the repeat. Stop and wait. Okay. And the reason for that is that stop and wait has good efficiency when we have low delay bandwidth product. The delay bandwidth product comes into the denominator here. And if this is small, then this is small, and we have pretty good efficiency. Okay. So the problem is when this is high, now, suppose that the delay bandwidth product is high, but the frame error probability is still low. What should we use then? Go back in. Okay, and the reason for this is that go back in when we have low probability of error is very close to the best efficiency we can ever hope for. So that's a good choice in that case. Now, what should we do when we have high delay bandwidth product and high error rates? Yeah, exactly. So, selective repeat for this. Okay, there is only one option left here. And that is when we have low and high. So low delay bandwidth product, but that high error probability. What should we use then? Pardon me?
What's the name of the first one we did, which was basically sending one?
Well, I mean, it's basically stop and wait. The one we did in the beginning without the sequence number doesn't work, so we shouldn't use that. But go back N is the one that we transmit. It's this one, right? Transmit and then wait for NAC.
Probably down there.
Yeah, exactly. So here I would choose stop and wait, which when we have a low T0 over TF is essentially go back N also. So this is approximately equal to go back N. Okay, but the efficiency of this will be similar then because N here, where would it go? Let's see, N here, which is T0 divided by TF, will be a small number. So the penalty for this is not so high. So then we can pick either one. Okay. So this is a little bit of a tricky part in figuring out the efficiency of the different protocols. This is not described very much in the book, so that's why I went through this in some detail. So if you have any questions on this, feel free to come and ask me later on, and I'll try to explain. But we still have a little bit of minor details to do before we are done with the ARQ protocols. So let's do them. First of all, if we have bidirectional links, that is, we transmit data in both directions, then what we can do is that the acknowledgements can hitch a ride on the information frames, and this is called piggybacking. So if we have data that goes from A to B and simultaneously going from B to A, then instead of transmitting separate acknowledgements from B to A, we can stick that into the information frame that we're also transmitting. And we get a situation that looks like this. So the frame that goes from A to B includes the data frame, and then also an acknowledgement, which anyways should go from okay. So B to A acknowledgement means that B would like, what the? Anyways, I think you get the idea that the acknowledgements that go in one direction hitch a ride on the information frame that goes in the other way or in the same direction. That's called piggybacking. Piggybacking is like you put somebody on your back and you run with them. So the pig is on the back, I guess. Okay. Anyways, we also need to say something about setting up the connection, because all of these ARQ protocols needs to be initialized with buffers and whatnot. So they're actually connection-oriented protocols. So we have, if you remember, we have connection-oriented and connection-less protocols. So all of these ARQs are connection-oriented, which means that we need to set them up. It needs to be a setup procedure before we can start. And here's a state diagram for going through this. I won't go through this because we're a little bit short of time. But yeah, that's how it is. Maximum window size. I just told you what the window sizes should be. And the reason why we would like to restrict the window sizes is to make sure that we are not unsynchronized between the transmitter and the receiver, in the sense that if the receiver and transmitter believes a packet with the same sequence number to be the same, but if it happens to be two different packets, we're in trouble. So maybe it's easiest to show this in an example. So let's do this very quickly. if we have go back n, then the send window size needs to be less than 2 to the power of m. And if it's not, we can have a situation like this, where we transmit packets, 1, 2, 3 packets, and then, or 4 packets actually. Here we have a send window size of 4, and we can transmit 4 packets. Now suppose all the acknowledgements here are lost for some reason, then at some point we will start to retransmit what's in the send window, 0, 1, 2, 3. But the receiver has already accepted packet number 0 up here, and now we'll see the same packet being received again, and we'll actually believe that this is the next packet which has sequence number 0. So the packet which is here will be delivered twice. Okay, so that's not good. So when we have 2 large windows, we can get duplicate packets. And this is the same for selective repeat, but there is a slightly different, very different mechanism. So I'll let you look through this. It's not so difficult. And then I think we will take flow control and the rest of the things at the beginning of next lecture. But the most important thing today was the derivation of the efficiencies, and actually to get this engineering insight into when we should select different protocols. Okay. All right, so see you next time.